Morning, everyone. So we are reaching pretty close to the end of the energy chapter. So far, we've been looking at mechanical energy. So this is energy that has to do with moving parts. Specifically here for mechanical energy, we've been looking mainly at kinetic energy, which directly is the energy due to motion. So you had a formula here, 1/2 mv squared. That's on your formula sheet. You can either say Ke or Ek for that. Kinetic and potential. Remember that word potential here means stored energy. We did one form of stored energy here called gravitational potential energy. Remember there are other ways of storing energy as well. Chemical energy, nuclear energy, energy stored in battery cells. There are many different ways, but we specifically look at the gravitational form. Basically, if objects were lifted off the ground, this would be how much is stored. Things that have energy, just a reminder, things that have energy have the ability to do work. Here. And remember, work is very stringently defined in this chapter here. Work is either a force being applied over distance, it's the parallel portion, or work is defined as a change in energy. Were it not for work done, the energy initial should equal the energy final. So those are what's referred to as mechanical energy. Today we're going to switch gears into thermal energy or heat energy sources. We're going to have a look at a few formulas that deal with heat transfers, heat going from hot to cold, and then we'll finish off with tomorrow's lesson on conservation. When heat is conserved and transferred between objects, we can actually make some predictions regarding temperature changes between objects. So that's sort of the direction that we're heading here. Today's topic here, we're going to just refer to it as thermal energy, the heat forms of energy. In terms of thermal energy here, we're going to start off with two definitions. The first one here is called internal energy. For some reason, they're going to use a symbol U for it. So internal energy, we're going to say this is the U of the system. As the name suggests, this is the energy that is internal. This is the energy that's inside the system. Whatever you are deciding to look at here, we'll refer to this one here as the total energy in the system. Now that total can definitely be, like we mentioned, it could be part kinetic, it could be part potential, it could be other forms as well. But this is the total energy that's inside your container. Turns out this number here is very, very hard to measure in real life because normally your system consists of many trillions and trillions of particles, and there's way too many ways that energy might be stored. But just to give you a feel for this one here, let's pretend we had a very simple system. Remember, the system is the part that we're deciding to study. That part there is completely up to us. In chemistry, this would be the reactants that are colliding, the particles that are moving. In this case here, let's imagine my system is fairly simple. We just have 3 individual particles, so I'm not having to add up tons and tons of particles. And let's imagine just focusing on the kinetic part of the system. So it's true when we have, let's say, this particle is made out of protons and electrons. There actually are going to be some background attractions. We're going to call those London forces in our chemistry course, but let's just ignore those for now, and let's just focus on moving energy. So let's focus on, let's say this particle on the top here is moving really slowly. Because it's moving slowly, I'm going to give it just 10 joules of energy. The second particle here is moving a little bit faster, let's say medium, and let's say it's 20 joules. And this last particle here is zipping by really, really quickly, and let's say it's moving really fast, and that's traveling at 30 joules. As you might imagine, for kinetic energy, the bigger the number, the more moving energy you have, the higher the velocity is. I'm imagining these particles are the same size just for convenience. In this case here, because we only have a couple particles, and I've only zoomed in on one form of energy, it's actually fairly easy for you to just go, okay, the internal energy, it's like going up to each particle and say, well, the slow particle here has 10 joules, second particle has 20, the fast-moving particle has 30. Well, in total, you guys have 60 joules worth of energy. That represents the internal energy inside the system. That's the energy that's divvied up between all 3 particles. We refer to internal energy as what's called an extensive quantity. Measurements in science can be either referred to as intensive or extensive. This is referred to as extensive because extensive quantities, they depend on the amount. They depend on how big the system is. If suddenly I go from 3 particles and I suddenly go to 300 particles, imagine going up to 300 particles, adding up all their individual energies. Of course, this number here will be much bigger just because of the sheer number, just because I'm looking at a bigger sample, suddenly the internal energy is larger. So that's what's referred to as an extensive quantity. Let's compare this to the next definition here. We're very familiar when we talk about heat transfers here. Let's take a look at temperature. Careful, we're going to use capital T for that. Yes, we used capital T earlier for period, so the time for one cycle. Lowercase t is definitely time as well, but in this context here, temperature, capital T is referring to temperature. And this temperature here, very similar definition like internal energy, but unlike internal energy, which is the total energy, temperature is actually defined as the average energy in the system. So not only are you going to need this total number, you're going to go up to each particle and add up all the little bits, all the types of energy that this particle has. So far I've simplified things just like a kinetic, but what this does here is this now takes an average. This now says if you stick a thermometer in the box, when the thermometer measures the energy, what it's actually measuring is actually the average speed that the particles have. At any given time inside my box, just because your average is something doesn't mean every single particle has to be traveling uniformly, has to be traveling at exactly the same rate. There's always some slow, some fast. If you want to look into it, you can look at what's called the Boltzmann distribution. But at least for an average energy system, I take this total number and I say, well, if in total we had 60 joules worth of energy, and I split it this time evenly between the three particles, well, it's sort of like on average, every particle is traveling 20. I'm thinking here, again, if you want to look up Boltzmann distribution, if you think about plotting number of particles and plotting your speed on the side here, we had one that was slow, one that was at 10, one that was at 20, one that was at 30. If I now imagine I average over many, many particles, I'd imagine the curve looks something like this, where when my temperature says my reading is 20 joules, on average, the most particles are traveling at 20, but that's notwithstanding here, you might have some particles that are slower, you might have some particles that are faster. That's always true. The temperature just gives you some average. This one, temperature here is nice because unlike extensive quantities here, temperature is referred to as an intensive quantity. So intensive quantities here does not depend on the amount. You can look at a big system or a small system, and because this one here does not depend on amount, this one here typically we say is useful for identification. Depending on what elements the sun is made of, identification. Depending on what elements this thing is made of here, the numbers are attributed to that particular chemical with that particular bonding. If you happen to have the numbers, you can match it up on databases here and you can actually identify what the chemical actually is. So for example, the melting point of ice. So melting point of ice, this one here is known to be 0 degrees. So whether we're looking at a small block of ice or a big block of ice, by the time both of them hit 0 degrees, both of them will start melting. Now, of course, extensively here, when we have a smaller mass and a smaller volume, there's going to be a smaller, I'm going to use Q for heat transfer. Just a smaller amount of heat is needed to melt that object because I have less to melt, and yet both of them are melting at the same temperature. If I have a bigger sample here, think about your internal energy would go way up. I have way more particles. Imagine adding up a whole bunch more joules worth of energy. But with the exception that we are having to add in tons and tons of heat, a bigger heat transfer, this 0 degrees here is intensive. I can look up a table of melting points and I can look up what chemical here is known to melt at 0 degrees, and I can try to match it up to try to identify, oh, this is just water, this is just H2O. So that's what we like about this temperature reading here. Temperature is something that thermometers measure. We have 3 very common temperature scales. So I just mentioned here in Canada, we use a lot with the Celsius scale. How we designed the Celsius scale was actually using water, because water was a very common chemical, really plentiful, really important to life. We set when ice melted, we called that point there 0. Let's go 0 degrees Celsius. That's the melting point of ice. Ice implies water as a solid. We figured out when that liquid water here ended up boiling point of water. We called that 100, and we ended up separating the scale here into 100 spaces. That's actually where we got our Celsius scales. Because water was something that was completely arbitrary, you may have some temperatures that are hotter than 0. You may have some negative temperatures. In the wintertime, we get down to -5, -10 or so. That's because we're actually just lower than when water would have frozen or when ice would have melted. So that's 0 degrees. Across the border here, if we look at the States, they typically use Fahrenheit. So again, they use degrees Fahrenheit here. We're not going to do Fahrenheit too much, but just for comparison's sake here, they similarly go melting point of ice. They put down here, I believe the number is let's look it up, 32. So 32 Fahrenheit here is their melting point of ice. And then for 100 degrees, they put down, if you've done any baking, 212 is corresponding to 100 degrees. Your ovens can go up to 350, 375 or so. All of those are measured in Fahrenheit. You can definitely convert back over to Celsius. We would look at this and we'd say, oh, Americans are weird. Why 32, why 212? But that's actually how they separated their scale. In a similar fashion, their zero would be a little bit lower than ours. So they do reach 0 Fahrenheit somewhere down the way. Again, you're going to have positive energies and negative energies, just depending on whether you happen to be hotter, moving faster than what's measured at 0 degrees. There is a conversion factor between the two of them, but again, we're not going to do too much with Fahrenheit. What I just wanted to show you were these are two common scales, and also a common problem with the fact that both of them have some positives and some negatives. It turns out when we actually look at temperature, because temperature is a measure of average energy, and we've already been saying energy is a scalar. Scalars here are not supposed to have direction. Scalars should always be positive. We actually run into a problem. If my temperature starts dropping into the negative, suddenly it starts looking like my energy is negative. Now, back when we were doing roller coaster style problems, we were saying, let me just draw that diagram for you again. We were saying the universe was a huge place. We have the system. We'll deal with this picture a little bit more in tomorrow's lesson. We were saying, yeah, sure, energy can be positive when it's heat in, energy can be negative when it's heat out. That's not what we're talking about here, because what we're interested this time is we're saying, let's just look at this system. We're not looking at a transfer. We're not looking for how many gain, how many loss. We just stick the thermometer directly in the system. And what I want is that thermometer to actually track the average positive energy that's inside my system. It wants to track, well, some are slow, some are fast. If I redistribute and I evenly kind of spread the energy amongst the particles again, I want to know what the average energy is. So that one there has to be a positive number because it's a scalar. In fact, if you go on into physics, you're going to find that the kinetic energy, I'm not going to give you the whole formula, but the kinetic energy is actually proportional to the temperature. Because energy is a scalar, energy here is supposed to be positive, then temperature better be positive. Which means that I don't really like, in terms of science here, although Celsius and Fahrenheit are very common everyday scales, I don't like a scale that arbitrarily has positives and negatives just because we set water as our reference. So in science, you probably remember what we do here. I think you learned this in Science 8. We come up with a whole new scale, and all we're going to do is we're going to reset the zero. The whole problem of the Celsius scale was we put 0 for water. That means there were temperatures that were hotter or colder, positive or negative. What if we reset that 0 here to the absolute coldest point? We're going to call that point there absolute 0. That's why we can typically call this the absolute scale. And we're going to call this one here OK. No, not OK. Just 0 Kelvin. So Kelvin is our scale. Notice it's not for whatever reason 0 degrees Kelvin. We just say 0 Kelvin. That's all we do. We reset our reference point, just like we did with potential energy. That 0 turns out to be more convenient. And that way, because this is the absolute coldest point, it's a theoretical point that we've never gotten to, then therefore all the temperatures from now on out have to be positive, and we've taken care of that problem. Because energy is a scalar, the average has to be positive. No problem, this could be positive. Just for curiosity here, we've gotten fairly close to 0 Kelvin. Probably, I think, as in my readings, we've gotten to like close to a micro Kelvin. Basically, we've managed to pull so much heat out that we're like 0.00001 Kelvin step off this absolute zero. But the problem with absolute zero is the particles would actually stop. So particles, this is a theoretical value, would stop. So you can imagine particles, again, a little bit of chemistry here. Let's say we have positive protons, we have electrons that are supposedly in orbit. As you cool things down, we know particles move slower. Imagine these electrons start moving more and more sluggish as we get closer and closer to absolute zero. As I gradually slow the particles down, if I theoretically hit 0 Kelvin, it's like completely taking away all the kinetic energy. Now the electron has completely stopped moving, the protons have completely stopped vibrating. And now it's actually a dangerous situation because the positive likes the negative. Sure, there's still a little bit of stored energy between the two here, but there may be some implosion. The electrons may run into the protons, and then even our atoms might implode. So It's not actually a good thing if we could hypothetically reach absolute zero, but that's a theoretical value useful for measurements. Fortunately for us here, we do call that the absolute scale here. It's all positive here. The Celsius was already gaining ground as we designed the scale here. So we decided to preserve the steps on the Celsius scale on the Kelvin scale. So when we match it up here, this was actually derived using gas laws. Even though it's a theoretical value, we can actually figure out it's actually 273 steps below water's freezing point or ice's melting point. We have negative 273, which means that if I reset my zero, the 0 degrees Celsius would correspond to 273 Kelvin, 100 degrees, 100 more steps off of that would now be 373 Kelvin. Again, notice that it's not degrees Kelvin. So what we've done here is, just like with potential energy from before, because we've reset the reference point, there's no doubt the numbers themselves are changed. 0 is now matched up with 273, 100 is now matched up with 373, and we now prefer this Kelvin scale because all these numbers here are at least positive. Now just a look ahead to our formula that I'm going to introduce you later on here. Turns out our formula later on is going to track a term called delta T. It's going to track a T final minus T initial, although I'm showing you on these scales here, because I reset the 0 point, the temperature numbers are different. 0 is now 273, 100 is now 373. At least the change will still be the same. So for example, if I ask you, how many steps are there between 0 degrees and 100? You can say the number of steps is 100 degrees, 100 steps. How many steps is between 273 and 273? Likewise, it's 100 steps, even though the numbers themselves are completely wacky, completely different, 273 and 373. So because in our main formula for Physics 11, we're going to look at delta T. Although Celsius is not the same as Kelvin, if we at least look at the number of steps on each scale here, same, just make a note to yourself, it's the same increment on a degree Celsius and a Kelvin scale. So you're going to find this be sloppy sometimes. We'll convert Celsius. Celsius cancels Kelvin. And that's only because in our formula, we're looking at change in temperature. We're looking at the difference in number of steps. Because we reset that 0 here, it's a very simple conversion factor here. You take your degree Celsius temperature, you reset it off by 273. Some people like saying 273.15 to be really precise, but 273 is good enough for us, and that converts us back to Kelvin. Because in science we use this absolute scale, especially when you do gas laws in chemistry here, you want to make sure everything is in the correct SI units. The correct SI units is actually the Kelvin for this heat stuff. All right. So that's just a little bit of background. We talked about internal energy. We talked about heat energy here. In chemistry, there's a very common term here called enthalpy. Enthalpy is also sort of like the energy in the system, but specifically looking at heat transfer. We're not going to need to worry too much about that here. We're just going to focus on heat transfer. So without further ado, I'm going to give you our main formula. This one here is on your formula sheet here. When we take a look at heat, heat is actually defined as thermal energy. So that's the amount of heat energy. That's another word for heat. Thermal energy that is transferred between something with high internal energy, something with either a lot of particles traveling really quickly. Conventionally, we'd say that's a hot object, to something with low internal energy, and traditionally we say it's a cold object. So we never have heat unless there's a transfer. So imagine I have two balloons here. One balloon is filled up with a really hot gas. That means the particles are moving really, really quickly. Fill up a balloon here with really cold gas here. Maybe the same number of particles, but moving a little more sluggish. I can't ask you, what is the heat of this balloon, or what's the heat of this balloon, because the heat isn't transferring. But when we have two objects and they're in close vicinity, heat actually tracks for us how the heat transfer, how energy gets passed from hot to cold. And like I showed you earlier, we're going to use Q for that heat term. So heat implies transfer. You have to at least have energy that's moving from place to place. This heat here, our formula is actually going to be MCAT. So you're going to go Q, lowercase, uppercase, doesn't really matter. Q actually gives us a comparison between three quantities here. It gives us a comparison between C, a term that's M, C, and then a term that's delta T. So these are three heat terms here. Again, on your formula sheet, I'm just going to write down for you what these terms mean. So Q implies here heat energy. Because it is a form of energy here, this will most commonly come to you as joules. Remember, sometimes you might end up using kilojoules. Just watch your unit conversions here. Sometimes this formula here, the M and the C are written separate. Sometimes they're written combined as a capital C here. If they're written together, this is just referred to as a heat capacity. In this case here, capacity. In this case here, because there is an M term, we can refer to the M part. Well, we know M. M is just mass. Conventionally, up to this point, we've been using kilograms because we've been looking for the weights of lawnmowers and elevators, things like that. Kilograms seem convenient. For this stuff here, when we're heating up stuff, usually it's joules. Usually it's grams that compares to the joule. Every now and then you will need kilograms. Just keep watch of what the other C term is. So this C term is probably the new one for you here. This lowercase c, so uppercase C, heat capacity in general was both of these terms multiplied. If I have lowercase c, which is separate from the M term, we can refer to this as a specific heat capacity. In science, whenever you see that term specific, it probably means that there's a mass term that's pulled out from it. So specific heat capacity here. This one here is actually, it depends on the material, and this is a constant that describes how easy it is to heat the material. So in this case here, specific heat capacity, this is the energy needed to heat. By convention, we go 1 gram. So if I imagine a box of this material, it could be water, it could be whatever chemical. If I imagine 1 gram of this material, and I want to heat that by 1 degree, 1 Kelvin, 1 step on the temperature scale, I want to know how much heat is needed for that. So I'm going to give you 2 constants just to compare here. The specific heat capacity of water, I do need to specify the state, because depending on the different state, it actually would be a different heat capacity. So in this case here, the heat capacity of water is actually going to be 4.18. The constant here is joule per gram Kelvin. So this is, it takes 4.18 joules. It takes that much energy to heat my block, which happens to be 1 gram, by 1 step on the Kelvin scale, by 1 degree on my thermometer scale. So that 4.18 here, this is actually where in food chemistry we actually get our calorie from. This is actually 1 calorie of energy. Let's compare that off the top of my head. I remember the specific heat capacity of aluminum. Aluminum is a metal, so aluminum is a solid. The heat capacity is only 0.90 for aluminum. So joule per gram Kelvin, it's the same unit, so I can make a comparison. If you take a look at the number here, in fact, the bigger the number, it's actually trying to tell you here, more energy is needed to actually heat up that same gram by the same degree. This one here, water, as compared to aluminum, is actually harder to heat up. So the material here actually will always have a specific heat capacity. The heat capacity number, the higher the number is, the more energy is needed to heat up that 1 gram by 1 degree. So it's even harder to heat up here. In geography here, we rely on this doing something called a moderating effect for us. So imagine we're here on the west coast, we're right by the Pacific Ocean. Imagine this is land, imagine this is the ocean. Because water is really nice, that water has a fairly high heat capacity, what's going to happen is we're getting pretty close to summertime. During the summertime, the sun shines a lot. Okay, it shines a lot of heat, everything gets hot. The land is actually going to heat up a lot hotter because ocean is made of water, and water's number is fairly high. The ocean is going to be some sort of moderate temperature. It's still going to be hot, but not as hot as the landmass. So what's going to happen here is, because the land heats up way more than the ocean, there's going to be a gentle breeze. You may not necessarily feel it as like wind. It's not necessarily going to be a very windy day or whatever, but there's always going to be a moderating effect. The ocean is able to get rid of some of the heat from the land because of this natural current towards the ocean. You can compare in the wintertime, it's the opposite. During the winter times here, everything is cold. There's not a lot of sunlight here, while the land has a lower heat capacity constant, so the land gets much colder, but the ocean, again, the same number is needed to cool it down as it needs to heat it up. The ocean will still be some medium temperature, still cold, but again, it's not going to be as cold as on the land. And what's going to happen here is, in the winter time, what's going to happen, we're going to have that gentle breeze go the other way here. Again, if you want to look this up here, in geography, we call this the moderating effect. And basically, because we're close by such a large body of water, the ocean is able to keep my temperature from getting overly hot in the summer times or overly cold in the winter times. So more of the story is stay on the west coast, right? If you go over into the prairies, once you pass the Rocky Mountains, you get closer to sort of Manitoba, Ontario. They're not close by large bodies of water, which is why they hit much bigger extremes in terms of temperature. Let's just try out a question here using this Q equals MCAP formula here. The last term here shouldn't really surprise you. For delta T, that's the term I mentioned earlier, this is the temperature change. And just like before, temperature change here is always T final minus T initial. It's a comparison of the before temperature and the after temperature. So let's just have a look here. Let's figure out here how much heat is needed to bring 250 milliliters of water, so that's a cup of water, from, let's take it from, maybe from the tap 10 degrees to 50 degrees. Okay. So the experiment is fairly simple here. How much heat is needed to bring this temperature up? So we're going to have our cup of water. It's like a mug of water. Unfortunately, they give us the water in milliliters. Nicely for us, we know that the density for liquid water is 1 gram per mil. Usually, sort of kitchen science, we always pretend, oh, mils is grams. That's actually only true for water. Water has such a density. So yes, if it is water, 250 mils is exactly going to be 250 grams. If I have things that are less dense or more dense, I actually need to convert it through density. So in this case here, it's 250. And I want to know right now, if I plop my thermometer in there, right now my thermometer says 10 degrees, and I want it eventually to say 50. So maybe I'm putting it on a hot plate or something, and I'm sticking it in a microwave, and I want to transfer the heat energy to actually heat this up. I want to speed the particles up enough so that the average energy on my scale now reads 50. So this is just a nice comparison of our formula. Q is equal to MC delta T. We're just going to punch in our numbers. Q is our heat energy. This time I want to bring 250, what would have been mils. I'm just going to show you the units canceling out here, 250. The C is the specific heat capacity. It's the constant for the chemical, how easy it is to heat up. On your formula sheet here, I'm going to give it to you as 4.18. Sometimes you just say 4.2. 4.18 joule per gram Kelvin. And then for the temperature change here, we're looking at what's the gap between 10 and 50. Technically speaking, I should be converting these to Kelvin. I should be adding 273. I should be making, oh, this is 283, and oh, this is 323. But seeing as our formula, again, is just a difference in temperature, it's just looking for how many steps do I want to increase it by. Well, I want to increase it by 40 steps, whether you convert it to Kelvin and then also count, well, 323 final minus initial is also 40 steps. Similarly, we're going to go 40 steps, and this is where we're a little sloppy. Sometimes we can say, oh, that's at 40 steps Celsius or 40 steps Kelvin, because I know it's the same step size between Celsius and Kelvin. Looking at our units canceling out here, notice this time I didn't convert grams to kilograms. That's because my specific heat was also quoted in grams, so that cancels out. Kelvin is not the same as Celsius, but in this formula, because delta T here is just the step size, how many increments, Kelvin does cancel 40 steps on the Celsius scale, and this now gives us the joules of energy that we need to actually melt this object here. Let's go 250 times 4.18 times 40. It gives me here 41800. 2 or 3 sig figs, so that comes out in joules. Many times we convert it to kilojoules. Remember, it's 1,000 joules make a kilojoule. So that's the number here. That's the amount of heat that I need to transfer for a mug of water to go up by 40 degrees. Now this is all perfectly fine. They can change up questions. They can be like, what if I apply this much heat? How much mass can I heat up? What's the constant if I know the other 3 terms? In general, we can always just find always one unknown. Now, one last thing I just want to introduce to you, we'll flesh it out a little bit more tomorrow, is let's just focus on, this part here was easy because water is liquid from 10 degrees to 50 degrees. What if we actually undergo a phase change? So I just want to do a quick recap here of kinetic molecular theory. So kinetic molecular theory, that's the notion that things are made out of tiny particles, not even in terms of atoms here, but because particles have kinetic energy, we assume that particles are constantly moving. So let's just remind ourselves the couple common states of matter here. We have solids, so the particles are just vibrating, shaking in place. They don't have a lot of energy. We can have liquid over here, and we can have gas. As a liquid, the particles are now overcoming some of those intermolecular forces. Same number of particles, but they're starting to slip and slide past each other. They're now sort of taking the shape of the container, whereas gases are definitely even the hottest. So basically, you've heated up enough. Every chemical will have a different boiling point before it sort of vaporizes like this. And in this case here, the particles are really wildly separated and really fast moving. You do want to know the names of these phase changes. So let's say solid to liquid. I'm going to show you them in red. In chemistry, we refer to them as endothermic reactions. In physics, we just say this is heat input. You need to put in heat for this to happen. Solid to liquid here, you can call that melting. Liquid to gas, hopefully you can say it before I say it here. This is called boiling. You could also say evaporating. I don't know if anyone's asked you the question, what's the difference between boiling and evaporating? Although both of them refer to going from liquid to gas, if I have, let's say, room temperature water, 25 degrees Celsius, I would say the liquid is evaporating, right? Over time, there might be the lucky odd particle. It just happened to breach the liquid, breach the surface tension. Remember, it's actually the air molecules that are actually pressing it downwards, trying to keep it in the container. You might happen to have one of those fast-moving particles, not all of them, there's only a couple of them. Fast-moving particles just come out with the right trajectory and just manage to leave. We call that evaporating. We don't call that boiling. We only call it boiling when we've heated it up enough as the particles, all of them in the bulk sample, as they all speed up. Once they all are traveling fast enough to actually go against the air pressure, that's when we start calling boiling. So in both cases, there's liquid to gas, but it's just a matter of whether the evaporating here is just a few particles, whereas boiling is the entire bulk sample. All the particles are now traveling fast enough for that to occur. There are some chemicals that actually skip the liquid state. Some chemicals transfer through it really quickly, but for example, carbon dioxide is known as this one here. Dry ice is actually solid carbon dioxide. Dry ice actually undergoes a sublimation reaction. Subliming is skipping over that liquid step. Again, it needs heat input. Let's go the opposite way here. Well, let's take away the temperature, let's take away the heat energy, let's cool it down. This one here will actually now be heat output, or heat being released. So gas to liquid, you can call that condensation. On a cool day, you can breathe onto a window and it fogs up, it liquefies, so it's condensing here. From liquid back to solid, you could say freezing, so that's where we get freezing point, freezing point and melting point from. So freezing, you could also call it solidification because I am making a solid. And I just mentioned here, every chemical, these are all physical changes. Nothing's happening to the chemistry. So water is H2O. After it liquefies, it's still H2O. It's still physical change. The temperature at which this chemical goes from solid to liquid, in this case here it's 0 degrees, that could be called melting point or freezing point. Just a matter of whether I am increasing temperature to melt it or taking away temperature to freeze it. Both of them occur at the same temperature. That's intensive. What if we went gas back to solid here? So gas down to solid. Give it color coding right here. In the past, I used to call this sublimation again. Sometimes they call it fugation. Nowadays, the most common term is deposition. So this is forming a deposit. Again, not all chemicals do this. Most of them will at least go through a little bit of liquid state, but there are some chemicals that actually go straight from gas to solid. So we had these phase transfers here. I just want to emphasize here. So phase changes or state changes. They like the term phase because sometimes you might be in the same state. I might be solid, but I might have different arrangements. I can call you ice that's in the first phase or second phase. Okay, so phase is like state. Phase changes here. These ones here are physical changes because nothing is happening to the actual chemistry of the molecule. So physical changes. What I want to just introduce to you here is if I went through a phase change, we can actually plot what's called the temperature time graph. Again, we're going to plot this out a little bit more on tomorrow's lesson. Let's imagine taking -5 degree ice. That means we have the ice just shaking there. And let's imagine the experiment is just, let's apply heat to it. Let's add heat so that the particles can now vibrate harder. Because we haven't quite hit 0 yet, that heat here is used to actually bring this one here back up to, in this case here, we have 0 degree ice. It's still in the solid form. If I did this experiment, I'm going to find, strangely enough, once I hit 0 degrees, my hot plate is continuously onwards. It's still trying to heat it up. But what's going to surprisingly happen is we're going to get a plateauing region. We're going to get a region where the temperature seemingly doesn't change anymore. The average energy doesn't go up. And then afterwards we go, whew, this one here does eventually climb again. So in this case here, we are actually using heat. If you look at the special temperature for ice here, it's actually occurring at 0. This plateau happens at 0. The same plateau happens when it boils. What's actually happening here is when we actually hit the melting point, the particles are actually starting to shake hard enough that when I actually supply the heat, it's actually not used to speed up particles to make them shake harder. I'm actually pulling it hard enough that this particle here is actually completely falling apart, completely ripping apart the structure. In fact, what we're going to do is we're going to take it from 0 degree ice, so 0 degree solid, to 0 degree completely liquid. So that's just water. So in that case there, you can make a note to yourself. We call these guys here temperature plateaus. So these are called temperature plateaus. And why is temperature plateauing at these special temperatures? It's because all the heat energy, it's not like I cut off the heat source and I cheated, that's why the temperature doesn't change. In this case here, all heat energy is used to change the state. In this case here, as I demonstrated, it's going from solid to liquid. It's actually a ridiculous amount of temperature that's needed to do this. I just want to show you the small change in our formula from earlier, Q equals mc delta T. Earlier we had said Q equals mc delta T. This works as long as there is some temperature change. Whenever I'm jumping up different steps on the scale, there will be some Q. But let's imagine having 0 degree ice and going to 0 degree liquid. In that case there, the temperature change is 0. Final minus initial, 0 minus 0 is just 0. That would seemingly imply that means no heat is needed. In fact, we just said there is heat that's needed. We need to overcome, again in the chemistry we call it the intermolecular forces, the forces that are trying to hold this particle here as one state. What we're going to do here is make a small correction term. And what we're going to do is, this is only during a phase change. If we're not at a phase change, the formula from earlier works fine. Q is equal to mc delta T. During a phase change, what we're going to do is we're going to hide this c delta T term. We're going to hide the fact that the temperature actually plateaus, and we're actually going to hide that in a new constant. We'll call it Q is equal to m. The hidden term here is now called L. The L is either going to be subscript F or subscript V. This L constant is just another number you can look up. This is now referred to as the latent heat. So instead of specific heat, it was C. This is now latent heat. If I use the subscript F, I'm talking about latent heat of fusion. Fusion is an old name for solid to liquid, or latent heat of vaporization. And that implies liquid to gas. So just to avoid the problem, there's no temperature change here, what's the heat transfer? I actually look up a different constant. So let's just end off with one last question here. I need to give you this constant here. So let's imagine how much heat is needed to melt. I'm just going to specify here 0 degree ice to 0 degree water. Just to imply this is when the temperature plateaued, this is when there was actually no difference in temperature. So what's going to happen here, I need to give you the constant. So latent heat of fusion, I believe off the top of my head here, this one here is 334. So let me double check my numbers here. Notice the constant here, the units are actually kilojoules per Kelvin. So the picture is pretty simple. We're going to have a 0 degree block of ice. We already are at the perfect temperature. We're now going to apply this heat here, just used to rip apart the structure. We're going to go 0 degree ice to 0 degree water, and the constant they give me, that L value to melt, is 334. So let's try it out here. Because we are already at the melting temperature, I can use Q is equal to ml right away. I just need to watch my unit here. I guess I should specify a quantity here, melt 0 degree ice to 0 degree water. Let's take that same 250 grams from earlier. That one would have to be given to you. So this time, unfortunately, because this is 250, it's expressed in terms of grams, that doesn't match up with kilograms. So either you convert this constant, so it's referring to grams, or you convert this constant here, so it's referring to kilograms. It's probably easier the latter. So let's go 0.250, that would be kilograms, times it by the constant 334. I don't know if you can see just by comparison here. This number here is actually fairly big. If I go 0.25 times it by 334, that's actually 83.5 kilojoules, or some 83500 joules. That's a ridiculous amount of heat. That was bigger than the number from earlier. Earlier, we had already heated up going from 10 degrees to 50. This is now a huger amount just to take 0 degree ice to 0 degree water. In fact, what I want you to end off with here is, let's assume, just to put that in context, assume this 83500 joules is applied to 250 grams of 0 degree water. So how this question has changed is, we started from 0 degree ice just to accomplish a phase change solid to liquid. And now what I'm going to do is I'm going to apply a second 83500. It's now already water. We have 250 grams of liquid water. It's now 0 degrees. It now doesn't need to melt anymore. If we supply that same 83500 joules, so I apply the second sort of amount of that, If I supply that, I want you to calculate for me, because we're not in a phase change, Q is equal to MC delta T. Punch in 83500. This one here is going to be 250. You can use the 4.18. Figure out for me what is the change in temperature. If it weren't for the phase change, this temperature plateau, 0 degrees becomes 0 degrees. What is the final temperature that we're going to be at? I believe when I did this before here, this should end up at some 80 degrees or so. So just try it out for yourself, verify it, make sure you do your unit cancellations here, solve for delta T. You should be getting some 80 steps on the Celsius scale. So going from 0 degree solid to 0 degree liquid is the same amount of heat that would be needed to take the 0 degree liquid upwards 80 degrees to find temperature. So find out that temperature change, verify for me that it's actually 80 at the end. So I'll flesh this out a little bit more in the next lesson. If you have any questions, just let me know. Thanks, guys.